In this video, we're going to look at how to apply LeChatelier's principle to solubility equilibrium situations, as well as discuss the basics of water treatment and toxic ion removal from water, which is one of the most important applications of solubility equilibrium. To use a case study as an example, if we consider this city, which in Mandarin Chinese is pronounced Tianying, this is the center of lead production in all of China. As we know, lead used to be a very common additive in paints, particularly in red paints, until we discovered that high lead levels were linked with abnormal brain function, as well as spikes in the rates of cancer. So as a result, a lot of development as far as environmental modifications have been either decreasing the amount of lead that exists within especially water supplies, as well as looking for ways to remove lead from any contaminated sources. Now, the problem about Tianying in particular is that generally levels of development in interior China lag behind more of the major cities that most people know about on the coast, so Tianying does not have access to a lot of the latest technological developments, which means that the mitigations as far as waste management goes are sorely lacking. So in order to deal with this problem, we need relatively quick and simple solutions that take advantage of relatively simple chemistry. And the easiest way to get lead out of contaminated water sources is to use precipitation reactions simply by adding an ion that will react with lead in order to give us an insoluble precipitate and therefore get it out of the solution. So if we want to do this, we know that with poorly soluble compounds like lead chloride, we need to take advantage of the fact that this is an equilibrium and therefore shift the equilibrium this way to the reactants in this case, where the precipitate is, therefore causing the concentration of lead in the water to decrease and getting it in the form of a precipitate, which makes it a lot easier to remove. This relies on using something that we call the common ion effect, which basically tells you exactly what we're going to be doing. So what we need to do to use the common ion effect is add in a compound that also contains one of the ions within this equilibrium in order to force it to go in the direction of the precipitate. Now, obviously, we don't want to add a lead-containing compound like lead nitrate, for example, because that defeats the purpose of getting the lead out of the water. So instead, we need a quick and easy and preferably cheap compound that contains Cl- ions that is able to dissolve in water. Now, if you think about this for even about 5 seconds, you can probably come up with one that is very common and very abundant and no doubt very cheap: sodium chloride. So the way that this works is that if we put sodium chloride into a solution of lead-contaminated water, we know that because all alkali salts are soluble when we put them into water, NaCl is going to completely dissociate into Na+ and Cl- ions in solution. And again, we don't really care about the Na+ because it's not going to do anything, but adding in Cl- is going to increase the concentration of Cl-, and therefore, if we have more Cl- than before, that means that we would increase the reverse rate of reaction. So our reverse rate of reaction would increase because we have more chlorine ions, therefore more collisions with Pb2+, and therefore we're going to get the equilibrium to shift in the direction of our precipitate. Now, because in this case we're making the reverse reaction faster than the forward reaction, that means that overall more of our ions are going to come out of solution and less of them are going to dissolve, and therefore we would expect the solubility of PbCl2 to decrease. So not only does adding in a common ion, one of the ions that exist within the equilibrium, not only does it cause more precipitate to form, because we have more Cl- to react with lead ions and form the precipitate, but it also makes it harder for the precipitate to then redissolve back into the dissolved ions that can then poison the water supply. So the conclusion that we can reach here is that adding a common ion, one of the ions from the equilibrium, causes the solubility of the precipitate to decrease, which makes it easier to remove that. The problem is, of course, that this is an equilibrium, which means as long as we have both our reactants and products, this equilibrium will maintain itself, which means, is it possible to completely stop our precipitate from dissolving? Well, again, as long as the equilibrium is present, the answer is no. And the key to overcoming this problem is understanding as long as the equilibrium is present. And as we know, one of the requirements to keep a dynamic equilibrium system stable is a closed system where no matter can enter or leave the system. So consider a very simple solution to this. If we do not have any precipitate, so for example, if we actually take the lead chloride precipitate that we created from adding Cl- and we actually remove that precipitate, if there is no precipitate, that means that there cannot be a forward reaction, which means the reverse reaction, the precipitation reaction, is the only thing that we can do. And the way that most wastewater treatment facilities work takes advantage of this situation, where we have the contaminated water supply, and this is the water that contains the toxic heavy metal that we want to remove, in this case lead, is pumped into a reaction tank, and in that reaction tank, the ion of choice that we're going to add, so in this case, we can use OH- as in the diagram, or we can also add Cl- into our solution, is added in, which then reacts with the toxic heavy metal that we want to get out of solution, and then this is pumped into a second tank called a concentration tank, where the two ions that make up the precipitate are concentrated together by removing all of the clean, untainted water from this, and the only thing that would be left over here would be the precipitate. And if we take the lead 2 chloride precipitate that we have gotten out of solution and then remove that simply through sedimentation, because a solid will have a higher density, causing it to sink to the bottom. And if we actually remove this, where it was would be transferred to a sludge tank where all of the waste would be removed, then we have taken the precipitate out of the solution and therefore prevent any extra from dissolving, and therefore make it a lot easier to end up with pure untainted water. So that's the basics about how precipitation-based purification works, taking advantage of a very simple effect of changing concentration and the resulting shift that occurs because of LeChatelier's principle. In the follow-up videos to this, we're going to look at how different environmental factors can be changed, but also why precipitation purification is ultimately the most cost-effective form of water treatment.